Welcome back, and maybe welcome here for those of you who didn't attend Industrial Forum in the morning. I hope you all have had a good lunch, because now we are going to take off, and I would like to welcome Professor Danica Krajic at Royal Institute of Technology on stage. She is also one of the leading, and I would say key persons to lead the investment, huge investment that we now are doing in Sweden in artificial intelligence. So thank you for that. In her talk, and with her background from computer vision to robot vision, will she reveal the true story of Westworld?
Yeah, well, maybe.
Welcome.
Thank you. Thank you for having me. And I will focus for the next 45 minutes on research that we are doing at KTH, and also on some collaborations that we have done in large European projects with other than European partners. I think that nowadays, when we talk about robots, dependent a little bit from what area you come, it's not always clear what you mean by a robot, because it might be something that is a hardware combination of a software and hardware. And for lots of people, a robot might be also solely software. So I wanted to first define what I mean by a robot. And for me, a robot is a physical system that might be pre-programmed, or it might be autonomous, but it's always equipped with different types of sensors, and sensors are used to, in some way, guide the motion of the robot. And when we think about the old-fashioned industrial robots that have been around since 60s, last century, and look forward in time, not much has been changed in terms of how robots are built and designed. So most of the focus has been put on building robots that can move around, carry heavy things, but mostly these are bolted on the floors, assembly floors, and to a large extent pre-programmed to move in a very precise manner. When the trend started to change, although designing robots and building robots that have been inspired by biological systems have been around for quite some time, but if we think about applications of robots, assembly industry, and so on, I would say that the trend started to break sometimes in early 90s, when Amazon bought Kiva and used it to automate the storage spaces, where I would say new industry or new applications were born, apart from having then autonomous vacuum cleaner that you could buy. Mid-90s, let's say, Electrolux was one of the first producers of those. We have seen then the aspect of mobility being used to start to automate the processes. And this has been the mobility in terms of robots being able to move around in the environment. So I would say that that has been a change in trend sometimes then. Now, the interesting thing then is to see what has happened during the past 20 years. And it's maybe not so very easy to reflect, because, of course, one can see different types of robots being developed for research purposes mostly. But if you think about the consumer market, so the first robots that we had out there, again, around 95, 96, autonomous vacuum cleaners. 20 years after, an autonomous vacuum cleaner became Christmas present of the year, Årets julklapp, what we say in Sweden. So for 20 years, very little has happened, actually, when it comes to robotics and consumer markets. So the systems that we had back in 90s became cheaper, some of them more effective than the first ones we had, but the technology is basically still the same. Rather simple sensors integrating with some localization capabilities, having robots moving around and having only or fulfilling only a single task. Now, if we think about companies such as Amazon, and also some ideas we had already back in early 90s when I started to work with this, was that, well, during the 20 years, given that we solved the problem of mobility back then, we would have robots that would not only just move around in our houses, but that would also be able to pick up things, sort them. So if there are like socks on the floor or toys or whatever, robots would be able to interact with objects of different shapes, sizes, weights, and so on. And also, this would be used like home assistants. And I think when back again in the early 90s, we thought that that was a rather simple thing to do. Now, this video is about 3 years old, is my team preparing for the Amazon Picking Challenge. So Amazon went on from then having automated the storage spaces to trying to automate the process of emptying and filling the shelves. So although the shelves can autonomously move around, and one can use AI or planning to plan how these should move in order to minimize the consumption of energy and so on, and do lots of nice AI software on top of the whole process of controlling the storage space. This task is still done to a large extent manually. So there's still humans filling and emptying shelves. And it's not only for Amazon, but I would say it's like for all the food stores, for clothes stores. There are like very many places out there where we use lots of manual human labor in order to do simple mechanical movement of different types of items. Why is this difficult? Partially it's difficult because when humans do these types of tasks, we use the flexibility of our body. We are able to use more muscles than just those that we have in our arms. We use upper body motion and so on. And we can also very flexibly move around and also change the shape of our bodies dependent on what are the places or the areas that we work in. Apart from that, we also have perceptual capabilities. Apart from vision, we use also very much tactile feedback in order to adapt physical interaction with objects. So we have more than 2 fingers, like the robot in this case. We can actively control the posture of the hand. We can use both the cognitive knowledge in terms of like high-level knowledge of how identify objects and use this information in order to adapt what kind of force we use when we physically interact with the object. All of these things, low-level signal processing, all the robots are also equipped with sensors that we humans don't have. So we put laser and sonar so robots can have and reconstruct 3D information from the environment, something that we humans can't do with our senses directly. Still, even if robots can be equipped with better measurement devices, it's extremely difficult to get together the software and the hardware and solve the problems that range from low-level signal processing to then high-level decision-making and planning. Apart from this rather simple pick-and-place task, something that we humans do then without thinking, there is also a big challenge for physical human-robot interaction. So physical interaction with the environment has its challenges, but to some extent, robot interacting with items is potentially not as dangerous as performing different types of physical interaction tasks with humans. Now, why is this difficult? It's difficult partially because we humans are very good in understanding how another human that we collaborate with would act or react in different situations. We have a tendency of understanding to what extent we need to take more or less of the weight, dependent on the person that we carry things together with. And apart from only using then information from the force torque, so trying to understand how much of the weight somebody that we collaborate with is actually taking and so on and adapting to that. We are also very good in using body posture information, so processing the data visually and also at the same time using dialogue. So if we don't understand something, we can ask a person collaborating with how to and what to do next, how to act and how to plan. Now, this is exactly what we are trying to do. So we are trying to integrate different types of interaction modalities to achieve what we call natural human-robot interaction. But there are still challenges. There are still challenges because humans that are not trained to interact with robots actually need some time to adapt and have the brain also understand and plan what the robot will most likely do next if this is not something that is conveyed through natural human-robot dialogue. I'm not going to talk very much about the brain, but there is also an aspect of the brain and the fact that we humans have mirror neurons and have easier time to adapt to or plan what another human would do. But there is a big role also in the design of the robot body. So we don't design robots or build them to look like or be inspired by human body in order to reconstruct or reinvent or whatever human body. It's mostly because to make it also through the kinematic design more natural for humans to predict what and to generate motions that are natural to humans. And then the third part of interaction is also type of interaction that we, again, humans somehow do without always being able to explain how we do it. So this is just one of the scenarios, motivating scenarios for my PhD students that we recorded. So the idea was that, you are at home, you're baking bread, and you have a third hand or a robot helping you with potential ingredients that you need. And the interesting thing in a situation like this is that if a human observes you and if a human sees that you have lots of dough on your fingers, it's very easy for that human to understand that you need more flour in your dough. Now, how do we get robot to understand that? Even given the progress, the tremendous progress in computer vision during the past couple of years, the systems that can track human hands, human fingers in interaction with flexible objects, and that can also understand, whether it's sugar or flour or dough on fingers is extremely difficult. But the situations like this are situations or applications like this is really something that lots of people foresee for the future. Partially because we would like also to have assembly floors where humans continue to do things humans are good at, robots do things that robots are good at. But the interaction needs to be, again, natural and seamless in the same way as the interaction between two humans would happen. Apart from a robot just being a passive third hand and helping in a task like this, you might see this type of a scenario also as educational scenario. So maybe the robot is one, actually having all the experience of how something should be done, performed, how a dough should be made. So the robot is the chef that is then training or helping the human to train itself through the interaction and gives the instructions to the humans, to the human, what the next step should be, how the dough should feel between fingers and things like that. So there is a collaboration scenario, there is a tutoring scenario, and there is also a big aspect of then exchange of information. So how can a robot learn something through just by observing what the human is doing, and also how a robot can be used to instruct the human of how to do something better. Now, when we think about scientific problems that are involved then in studying or developing systems like that. For my area, there are very many, and they range when it comes to publishing, for example, from conferences that are pure computer vision conferences, AI conferences, machine learning, robotics, and of course, software conferences. So what is really important here is that then when it comes to development of the systems, there are very many researchers that are involved in these large-scale projects. And software, I would say, is in the heart of everything, although maybe some machine learning people wouldn't say that just the software in itself can do anything apart then from the methodology. Just to give you an example of one of the projects that was running for 4 years and finished up a year ago, RoboHow.cog. So the idea was to study or develop systems that would enable robots to learn from scratch how to prepare food. So the idea was to have a robot or to develop a framework, software framework that will allow a robot to use the information that we humans would use and that we have generated for our own purposes. So if I would like to prepare a new meal that I have never prepared before, what is the process that I would use? And can we use the same type of a process that can then enable a robot to do exactly the same? So basically learn from scratch. So the idea was that to use the information or the data that is available on the web. So in the same way as I would search Google for a new recipe, process textual information, see what ingredients I need, check whether these are the ingredients that I already have. If not, I would use maybe an app to order ingredients through a web-based store. And after the ingredients are delivered or after I prepare them, I would put them together or I would follow a textual instruction that you usually have on recipes that tell you how to actually put these ingredients together. Now, processing text is not a problem. Understanding the meaning of the text is not a problem today. What the problem is to really go from a text to an activity. So when the text says crack an egg or flip a pancake, what does that actually mean? How does the robot then go from something that is described in text to something that the robot needs to do with its own body? So the idea in this project was then to use YouTube and look for, let's say, visual instructions. So use then vision-based body tracking software and so on to try to extract information from videos, again, available on YouTube, to try to understand what is the outcome, for example, of an action called crack an egg or flip a pancake. Now, that was the first, I would say, problem we realized. Not so strange, but most of the examples we today have on YouTube are not positive examples of something, or rather negative examples. So people have a tendency of putting on YouTube bad examples or funny examples of things. So when you look for crack an egg or flip a pancake, you will actually get an example of something that fails, rather than something that is instructional. So the first challenge was really to understand what is a positive example, what is a negative example, try to understand whether we have the right amount of data. And I would say that the state of the, not state of the art, but state of the web is that we actually don't have the statistics, so we don't have the right amount of proper data so that we can, or robots can learn freely. So we still then, and during the whole project, relied a lot on self-generated databases and so on in order to make then the learning process feasible. I would say that cracking an egg is still an extremely difficult task, even if you can somehow describe it both from the process of, let's say, low-level sensory to the high-level cognitive, in terms of what the outcome of cracking an egg is. And as you know yourself, cracking an egg can be done in many different ways. Either you do it by holding an egg and then cracking it, or you use another tool to crack an egg and then divide it and so on. So I think that when it comes to then the future use and applications of robots in real-life applications, that's still a big challenge, having robots doing things or doing tasks that we humans do on a daily basis and we take for granted. Robots still don't have capabilities that are, well, or can to some extent mimic humans in everything that has to do with fine manipulation. So I'm going to give you a couple of examples of what the state of the art in this area is and how people are working then, or we in particular, with grasping in-hand manipulation and so on, and what the challenges are. But of course, I also need to mention, maybe it's very difficult to read now on the slides, but just to give you an idea. So this is an overview of the project and the different work packages in the project. It's not so important to actually read different parts and so on, but I would say that every box here, it's in a way different software base, and different software base because it's usually made by people that come from very different communities. Again, computer vision, machine learning, maybe classical AI, planning community, and so on. And then, of course, we always have some people that are really good in building software architecture for robots and so on. And I have been now in EU projects for almost 20 years, and I think it's really, really interesting to see that the difficulties of still integrating, let's say, new solutions, new parts of software in a completely working system. So we can potentially have a perfect body tracker or a hand tracker or something like that, but integrating it with the rest of the reasoning system is not, let's say, a plug and play, what we would say. So I think that when it comes to applications such as robots for domestic environments and so on, software development is extremely important area. But I think that right now we are at the, let's say, at a time where it's a little bit of a chicken and egg problem. So in order to know what kind of software or what kind of software architecture we need and how the software should be integrated in order to be able to standardize system, we actually need to be able to test them. We need to test them with regular users and in, let's say, real world situations and so on. And the problem right now is that we don't yet have commercial systems, commercial hardware systems that can be, let's say, deployed in large volumes. We work, as I said, very much with trying to understand also human interaction with the world. My particular area is trying to understand human hands. So how do we use our hands when we interact with each other, when we interact with objects around us, and so on? And what is the meaning of actually having 5 fingers? Should the robots of the future have only 3? Is 3 enough, and for what, and so on? And I think that it's really interesting that when I started this research, it was with the premises of really building the next generation of robot hands. But the areas that really got interested in results of this research was the industry for prosthetics, so prosthetic industry, where they build artificial limbs. Because when we look back for approximately 20 years, the hands were really heavy, but had only a single degree of freedom, so they maybe looked very anthropomorphic, but could only open or close. And in that market today, we have a tremendous change where we see hands where we can actuate more fingers, where we can also activate the motion of the hand with neural contact and so on. Other area that was really or is really interested of this research is also the gaming industry. So how can we build more realistic games where in the game you not only see how the object moves, but you also see a copy of your body and have a good understanding of how your hands would move in the virtual world in order to interact with objects, which also makes games a little bit easier to perceive by the brain. I would say that the development and the use of this research in these 2 areas have actually been much faster adoption of that research than in the robotics community. And again, a little bit motivating video, just to give you a little bit of a difficulty or a challenge. Maybe we don't do dishes as often as we used to now with dishwashers and things like that, but I think it's a very nice example of human ability to interact with objects and also, without really understanding the underlying physics of the process, adapt the motion to a changing environment. So you can't really convey or explain what is the exact number of, or the force in newtons that you use when you hold a porcelain bowl that is, let's say, covered with water, dishwasher powder, or oil. You know that you hold it harder dependent on what it is covered with, right? You know that, but you can't really put a number on that force. You also know that you're able to interact with 2 or 3 objects at the same time, so using sponge as a tool to do something with it and adapt also the pose of the fingers dependent on what you're supposed to do with that tool. Now, this is really interesting because if we would like to have robots doing something similar to this, and there is lots of industry today, that requires this fine manipulation from humans. Of course, things can be done in different ways, but just the fact that it's also for us sometimes difficult to think how we would do things differently if we didn't have fingers. And I think it's really interesting if you just do a test, go home and put a bandage on 4 fingers and try to use only 1 or 2 for a whole day and do everything you're doing on a daily basis. And you'll see how difficult it is and how much you actually need those 3 or 4 fingers that you think like you can compensate with the rest of the body. And it's not all that easy. So when one thinks of automating processes that right now humans are doing, like that require lots of manual labor and fine manipulation, it's not all that easy to do. Now, disruption is happening, of course, in lots of industries, including fashion industry. And you know that in fashion, it's lots about interacting with very deformable objects, fabrics. Moving that fabrics around, holding it differently dependent on the type of the fabrics and so on. So there we see that there is, let's say, a big penetration of trying to do things differently, so not so in the same way as humans would do. How easy or difficult this is to do, and for how many years it's going to take until we have robots doing something like washing dishes is difficult to say, but just to give you a little bit of a perspective. So the adaptation, so the video that is showing robot adapting how it holds something when the dynamics changes. So when the, for example, weight of the object or there are some external forces perturbing the object and so on. So there are 3 fingers involved, and you see that there is some finger gating going on. So reshaping of the grasp, something that we humans usually do when things start to slide in our hands. These green sensors that you're seeing here are filled with fluid and can measure vibrations, for example, can measure forces and so on. And we develop different types of control algorithms, both classical control and reinforcement learning, model predictive control. All of these things or all of these algorithms are integrated and used for different purposes here, to first identify what kind of perturbation happens, but also to adapt how the robot holds something. And the robot also needs to understand whether the object it holds, it's rigid or deformable during the interaction. So in principle, you can just apply more and more force when things start to slide. But if you hold a plastic cup or a carton filled with milk, which is open, you know that you cannot apply just about any type of force because you will start to destroy the object. So this learning and interaction that happens is both for the purpose of then holding the stable grip, but it's also for the purpose of identifying what are the properties of objects that I'm actually interacting with. And all of this needs to be done in real time. So I think that this is important to say because most of the things that robots need to do needs to be done rather fast. Most of the things are usually, or most of the software is usually based then on measurements that come from different types of sensors. And the problem with sensors, because there are problems, is that these are not as effective, I would say, as our skin and our nerves that we have in fingertips. due to the fact that they need to be recalibrated. So the fluid can potentially, well, disappear. You need to add fluid. You need to estimate the nominal parameters for the forces and things like that. So there are still very many challenges apart from not being able to have as many measurements as you would get from a human fingertip. And also the cost. So these three, just the fingertips, cost around 25,000 euros, and then the hand costs twice that much, and then the arm costs blah, blah, blah. But you understand. So deploying these products on the market, it's not only about making them able to some extent, execute or demonstrate kinds of tasks as humans would do. It's also, of course, the price. Now, when it comes to then addressing the scientific issues and so on, this is also something that I would say robotics community is very much motivated by the software community. It's, of course, benchmarking, trying to find ways of how we can generate different types of benchmarks so that people can compare their software solutions or methods on the similar kinds of tasks. To some extent, this is still very difficult in the area of robotics because most people will not have the exactly same sensors or the exactly same hand or the exactly same arm. And even if they do, in many cases, these will not maybe be calibrated by the same software and so on. So there are lots of difficulties still in benchmarking solutions when it comes to advanced hardware-based systems. Of course, one of the things that we also see as a trend in robotics community is development and the use of different types simulators, because generating the data for the learning algorithms, and I think Jan Bosch has talked a little bit about that. In order to be able to generate the data, one needs to train a control algorithm or something like that. The robot actually needs to interact with lots of different types of objects in many situations. But the problem is that robots are not yet as robust as we would expect them, which means that they very usually, commonly break. Sensors break also, so if you if you are not skilled, for example, in control or reinforcement learning and apply a little bit too much of the force while squeezing a bottle or something like that, it's very likely that one of those syntax sensors, the green ones, will break and so on. So for that reason, in robotics community, we see an extensive use of simulators that are based on rather extensive physical, let's say, modules. But as in car industry, I would say that that's rather good, but doesn't work always. And I'm not going to go very much into the basic mathematics, but the soft point contact is still something that is mathematically not solved. So having two soft bodies interacting, so that's most of the simulators out there are not good in simulating that very realistically. So there are still challenges. There has also been mention about deep learning today and machine learning in general entering very many fields. And when it comes then to robots, it's very natural to compare and see, okay, if we can do, or if we can have systems that are better in categorizing images than humans, if we can have systems that are better in understanding speech than humans are, why is it so difficult to then have robots that can do everything that humans can do, then based on this visual feedback and speech feedback and so on? And if I can explain it with one example, then this is this, okay? So if I present you this image and I ask you whether to categorize each image, whether it's puppy or a muffin, it does take some time, right? You go back and forth, you look at the images maybe several times and so on. And sometimes it's extremely difficult also for humans to explain what is exactly the features or the parameters you use to make your decision. Why image 1 is a muffin and why image 2 is a puppy. So what is indicative, what is descriptive information in the image that actually defines this? Today, artificial systems or computer vision software is better than humans in doing this. You can present a set of images to a software, and it will do this categorization faster than a human. But what does that mean? Does that mean that I can use exactly this software now and plug it into my home servant robot who is serving me breakfast? Does that mean that the robot will be better than any other human in finding, detecting what's a puppy and what's a muffin and serving me a breakfast? No. So this is what we are seeing today. Now, when we think about robotics, we need to have a holistic view because the robots that are deployed in natural environments, rather dynamic environments, where things move. Muffins don't move, puppies do move. So decision-making is much more complex than just by using a single sensory modality and identifying a specific item in an image. So while this solution may potentially work for Facebook to develop a software that can categorize your images or your pictures after being at vacation, it's not probably the same and not even similar software that we can use to deploy robots that help humans in natural environments. And why is it so difficult? Wanted to give you a couple of examples. So if I have a robot with 3 fingers and I would like to develop a robot that somehow interacts with human, has a physical capability of physical interaction, and just basically serves things. So what is a good grasp? How do we understand whether a good grasp is described as something stable? So it's very important for a robot to be able to actually hold an apple. Or is a good grasp that is a grasp that is both stable but also has some contextual understanding. So if the robot is to give an apple to a human, then it shouldn't completely encompass it in its hand, right? So it should apply a grasp that allows the human to actually take that object from the robot. So how do you describe this for every single object out there? And it's even more difficult than that, because if the robot is to do this completely autonomously, it's given a task, robot, bring me something to drink. Rather easy to understand grammatically. Or if I say, robot, bring me something to drink from. It's a very different kind of instruction, completely different type of task that I have instructed a robot to do. Now, if we look into parts of the systems that are needed in order to be able for a robot to do something really, really simple, such as this, the robot needs to understand where it is. It needs to understand where the object that I'm searching for can be found. It needs to be able to move between where it is now and where it needs to go and pick up the thing that I send it to pick it up and so on. It needs to be also able to know something about my preferences. So if I want something to drink, it might range from everything from water to a soft drink to if I'm angry or depressed or something like that, the robot may even suggest something else. So it goes from everything, from situational kind of like understanding, individualized personal understanding, preferences, and so on. So if we would like to have robots that really do things that a human helper or something like would do, there are still many challenges that need to be addressed. And that's not always so easy to see. So when we look for really amazing robot videos, you know, robots from Boston Dynamics that jump and are able to keep stable on the ice, and can do they can do jumping and rotation in the air, and they have both legs and so on. There's still videos that demonstrate only a single thing. There is very little interaction with the human user, and there is very little understanding of situational kind of understanding or contextual understanding. Now, how do we get there? Of course, apart from then, as I said, understanding the physical work, the physical world. Let me jump over this one and maybe just focus a little bit more. I think I have 5 minutes left or something like that. I wanted to show you then and focus on the aspect of physical-robot collaboration and what has changed. So when we started to do this work 10, 12 years ago, well, the deep learning was not yet there in the way that, or let's say, we couldn't make reinforcement learning tractable because the processing power wasn't there, but the theory was there. So we looked into that in parallel to the control algorithms that were much easier to implement, but that requires some form of understanding of the physical process. So we needed to understand how to model things in order to be able to then say that this system will always behave in this way. And then when we started to work and implement something that was based on, for example, reinforcement learning, and we started to look in exactly the same type of task. How can a human and a robot carry something together, but then not use model predictive control or optimal control, look more into how we would generate from models from many tries and having human and a robot doing things in a kind of like more playing setting and use this as the basis for training reinforcement learning algorithms. So this is where we are today. We are very much looking into both technologies or both methodologies from different areas. We are looking into what is the dimensionality of the problem we can solve, how much we need to know. So this is completely reinforcement learning now. A human and a robot have never played. This is the first time they're playing. And the goal of this task is basically to balance the ball in the middle of this thing that they are holding together. So without really understanding the nitty-gritty bits and pieces of and building an analytical model, we generate lots of data and train reinforcement learning algorithms without forgetting about that this can also be solved by model predictive control, for example. But what we are interested in is looking into the scaling capabilities. So what is the dimensionality of the problem that we can solve with more classical methods and then learning-based methods? What are the data that we need, how this data is generated, and so on. And the other part is also the aspect of trying to understand the human motion and having a better multisensory interaction. So the video that I just showed uses force torque feedback. But then, of course, given the developments in the gaming industry, the fact that we can now very easily use gaming software from let's say, gaming consoles and so on to track human body and add hand tracking, for example, we can also understand better how human motion can be predicted. And the prediction, so what the human will do, is also important for the robot in the same way as it is important for the human to be able to predict what the robot is going to do next. But given also the fact that we can display in an easy way what the robot thinks of doing, because we have a forward model, and that model can be let's say, displayed visually for the human. The vice versa is not so very easy. So we humans are not actually very good in describing how we will move, not in a way that it's easy understandable by the robot. You never use words such as, oh, I will move my third joint for 15 degrees and the fourth joint for 2 degrees and so on. We just say we will move left, right, I will lift things and so on. So trying to understand these different types of how information is conveyed and how to then integrate this to build also better prediction algorithms so that the robot can predict what the human will do. For that, we use lots of deep learning. We look into methodologies that, in a way, can predict very natural human motion. in different situations. This is done from different type of mock-up data and so on. And all this information can then be contextualized so that dependent on what the human and the robot are doing together and so on, we can make it easier for the robot to say that the most likely thing that the human will do next is this or that. And then the robot can act effectively dependent on that information. So let me then just end up with a couple of things what we are going to see more. So given the developments in deep learning, today is not anymore about implementing CNNs or anything like that. It's about putting together different types of deep network structures with something like generative adversarial networks and reinforcement learning, and really try to understand the dimensionality of the problem you're trying to solve and getting robots to learn things directly from interaction. So these are just two examples that I wanted to show here where the robot is tasked to throw a ball and hit a Pokemon. And what you see here is, it uses you don't see it, but it uses 7 degrees of freedom arm. And controls that arm in real time, dependent on where the human has put the Pokemon. So if you think about the dynamics of that system, is actually quite advanced in order to try to, let's say, estimate both then with what velocity to move each joint, when to drop the ball, what the trajectory should be, of course, dependent on where the Pokemon is. So this is something we do with, again, reinforcement learning and deep nets, and I think that everything that has to do with dynamics, we're going to see more of these integrated frameworks being used and applied in robot systems. So I think that maybe I should stop here, but to relate a little bit to both the hardware and the software development. I don't think that these two can be seen apart. I think that the development of software is very much dependent on what type of body you're trying to control and what type of sensors that body is equipped with. And I think it would be really, really interesting to understand for every type of combination of body design and the sensors, what is the effective set of behaviors that a certain robot can exert. When it comes then to different types of modules and tasks or the behaviors that I'm talking about, I think that is extremely important then to have a holistic view when one starts to work with this. So not only think of, there is a robot and the robot is supposed to clear the floor. Yeah. But for the future, we are going to really need to understand lots of different types of algorithms that actually need to work together. And how do we understand whether a high-level decision-making system is the right one given the basic software that we have for image segmentation, object detection, object tracking, and so on. So when we talk about verifying software, when we talk about what Jan Bosch has been talking about, having lots of simple units that are just then integrated. Well, that was not Jan Bosch, that was, I don't remember the name of the gentleman before him. But anyway, I don't think that that's all that easy to do in robotics because I don't think that you can simplify things too much. And the reason for that is if you think about just the structure of the hand, how many fingers it has and so on, it's extremely difficult to say that you will have a software that just is focused on controlling the motion of a finger. Because if you want to then talk about the stability of the grasp, if you want to talk about adaptation and so on, you actually need to take into account all 5 or 3 or whatever one has when it comes to the number of fingers on a robot hand and so on. So I think that for the robotics community, how simple you can go, I think that this is still something that we don't have a clear picture about what are the different levels. of that. And of course, right now, many people would like robots to remember everything, and once they are told to do something, they should never forget about that, which is also very difficult, right? Because this is not something we humans do. We have a tendency of learning something and then forgetting about certain things and using the most or the latest software that we acquired or something like that. And this is still something that it's not discussed very openly, I would say. So can we have robots that forget things? Or do we solve everything by just using the cloud and so on? And of course, these multisensory systems that are measuring and acting things, and in many cases the sensors are also redundant, so measuring the same things. How do we understand that through basically software development, and how do we also use it to use the software to standardize things in the best possible way? So thank you. Yeah?
See if, yeah, now you can hear me. Thank you for a brilliant, mind-blowing talk. I think we might have some questions in the audience, so please line up. We have already one.
One, at least.
Yes.
Yeah.
Please come up. And in the meantime, I'll actually quickly ask this. So you have mentioned a number of challenges in terms of achieving that interaction that we really are trying to achieve. What's on the bright side?
No, I think that on the bright side is actually the possibility for disruption, so that we can have systems that can do, as we usually say, 3D jobs, dirty, dull, and dangerous. So all those things that are not developing for humans, things that were our bodies and so on. So if we can have robots to automate things that humans should be doing in the first place, I think that that's actually a rather positive thing. So, of course, there are certain jobs that will disappear, but I also see that maybe with help of robots that have the ability to physically augment a human, lots of jobs will be also made different or easier. Plus, now I haven't showed it, but there is this picture that I commonly use where a human and a robot sit side by side in an assembly line. So, as I said, humans are doing the things that humans are good at, maybe some high-level, decision-making and so on, while robots are doing the things that robots are good at, maybe exerting very high force or cutting very straight lines. But a robot is only a computer, if you want to see it like that. So you can also use it for increasing or having a quality of interaction. So if this is a human that just moved to Sweden, doesn't speak Swedish, the robot can actually be used at the same time when they are doing something that is very mechanical to conversate. So we are thinking about, lifelong learning and things like that. So I think it would be really, really nice to see this kind of creative ways also of using robots to add on something, not just thinking, oh, my job is going to disappear. No, your job can be made different, better.
Yeah, so to amplify
So that would be kind of like the positive,
Yeah, excellent. So Pekka, please.
Thank you for the presentation. My question is that, is it okay to kick a robot dog? And now the question, now you think about the answer is that, of course, the ethical concerns. I look at the challenges and I don't find this this angle raised. So how do you deal with? How does your team deal with ethical choices?
So it's I think it's a difficult question and very multidimensional question. So is it okay to kick a robot dog? I would tell you, as a head of the lab that maybe just bought that robot for 2 million euros or something like that, is definitely not okay to kick it.
Not touch my robot.
Because, no, but you understand. I mean, okay, there is a very practical price aspect there. But I think that I would say the way we use and develop machines is also now coming to a point where we need to talk about things that we as humans have very difficult time talking about, ethics and moral. And that, there is no red book of ethics that is valid throughout the world, and the same is valid, for the moral. When we talk and when we say what we think about things, we always try to be the right citizens and so on, but on a daily basis we do many things that are not maybe good for the environment, that are not good for our neighbors and things like that. Now, this is coming to a surface, right, with the machines, because partially machines are doing things that we do on a daily basis and potentially also making decisions instead of humans. And I think that this will be the first step. So I think that kicking the robot and discussing whether, the robot has consciousness and things like that, that would come after. But if I'm now to be a little bit kind of, I don't know what, very open, let's say like that. Let's say now that, one of the industries that is pushing very much for the development of human-like robots is sex industry, right? Because you want to build robots that look in certain ways and are equipped with all sorts of different sensors and things like that. If you can use robots instead of humans to solve the prostitution problem, to solve the white slavery problem, and so on, is that okay?
Thank you for the counter question.
Something to discuss in the coffee break.
Yes, aperitivo is for this. Thank you. I will let the next question.
Yeah, thank you, Pekka. And please state your name as well. Welcome.
Hello. I'm Mika Mäntylä from the University of Oulu. Great talk. I don't know very much about this, but I'm just wondering, when are the robots coming to home? I mean, filling up the dishwasher and cooking a meal, it's very repetitive. You do it on a daily basis, and it's quite simple. With simple hand could do it if you could adjust it to the kitchen table.
Yeah.
So what's preventing that these things are not home already? Because it's
when I started my PhD back in 1996, 97, the first project that we had was collaboration with Electrolux. And I don't know if people remember, but they had kind of like two grand ideas. One was the development of the autonomous vacuum cleaners, and we see how that progress has gone, right? Great stuff. And the second one was smart homes, integrated homes, where these mobile devices were kind of like connected and blah, blah, blah. They were too early. So I think that with lots of technology, we have great ideas, but sometimes we are just too early in terms of believing what people are willing to pay for and buy. And I would say that this is one aspect of it. We are not willing to change our homes to be able to use the technology as is today. So we would like to have our homes designed as they are, and just then have things that, move around like we do, like we can move from place A to B, have a certain size, are silent, and so on. And systems are not yet there. And I think that it's a little bit chicken and egg problem. In order to be able to do better design, you need to buy something, you need to pay something, lots of money, like we did with first vacuum cleaners that costed like, what was it, 1,500 euros, I think the first one costed. Yeah. And today, that entrance price would be just too high. So we don't have systems that are on the level where the volumes can be so high so that we can incrementally introduce them as we did with vacuum cleaners. So maybe when cars don't cost us anything, then we will be willing to invest in something else. And how long time that's going to take, I don't know.
That's an interesting...
The price right now.
Interesting suggestion from a systems thinking approach, actually. That's my background. Thank you for the icebreaker. We suddenly have a lineup.
Hi.
We have about a minute. So
okay, so I'll be very short in answering. It's my fault.
Come on, Ivica.
Ivica Crnkovic from Chalmers University. So you mentioned software and hardware design and development at the same time, and software is like much easier to change. And is that development then limited by hardware? Can you make solutions which are like general for any type of hardware, or how do you change hardware? So how do you
Precisely. I would say that agility, in a way, we see it today also in hardware, partially because of 3D printing and partially because people understood that making something out of very many similar or same modules is doable. That was not something that ABB or KUKA maybe thought of 50 years ago, but due to the way we can produce things today, the design is changing very much. So is actually following the module kind of precisely, very much like that.
Thank you very much. I must ask you to save your questions for the aperitivo.
Okay, I'll be there.
Yes.
So yeah.
I'd like to give you some Swedish chocolates.
Okay, thank you.
Thank you very much for joining us here today.
Thank you so much.